Let me see. Is my audio on?
Yes.
Okay, thank you. So last week we discussed unsupervised learning algorithms, and we covered KNN, Kmeans algorithm, DBScan, and a host of others. So today we are going into Gaussian mixtures. So Gaussian mixture model is a popular unsupervised learning algorithm, right? And the approach is very similar to K-means, but the only difference between Gaussian mixture model and K-means is that Gaussian is more robust and it is a bit much more complex and time consuming than K-means algorithm. So we are going to look at the weak points of K-means and how Gaussian can actually help us overcome all these weak points. So in K-means algorithm, clusters are always circular. So like we have here, you can see that there are like how many clusters? 1, 2, 3, 4. There are 4 clusters here. They are always circular. And this is because we are using a single point in our feature, which is like our centroid, right? And this point is also known as our cluster center. Now, each point is to the nearest cluster, right? Based on the Euclidean distance. Now, stay with me. The covariance value of K-means is always 0 because we are not making use of any covariance value. We are just making use of the mean, and that is calculated based on the Euclidean distance. So if for Gaussian mixture model, it takes different types of shapes, and that's because it has a covariance value. So if you are paying the extra cost of computing a covariance value, right, you won't make use of K-means algorithm anymore, because since you want to have like lots of different shapes, and since you want to have like a better result, right, make use of K-means algorithm anymore. So that's why we now have Gaussian, because we are not just calculating the mean, we are also looking at the covariance value and some other parameters. So the next slide, when are we to use?
Let me just interrupt you a little bit. Do you mind maybe going back to your slide for K-means, just to explain, since Abby is joining us sort of in the middle, like what
Okay.
K-means was? You don't have to spend too much time on it, but I think it provides good.
Okay, so let me just go from the beginning.
You don't have to go that far, but just quickly, like in maybe a few minutes, because we want to focus on Gaussian.
Okay, so K-means is an unsupervised learning algorithm, and when something is unsupervised, that means you don't have the labels defined, right? So you have like the data set is given to you, and you have to just form them into different clusters. So there are different types of unsupervised learning tasks. We have the clustering, we have anomaly detection, and then we have density estimation. So we can use this clustering. We can apply clustering to customer segmentation, right? So if you have like lots of customers and want to understand where each customer falls into, maybe based on the goods that they purchase, we can make use of clustering algorithm or data analysis to analyze data, dimensionality reduction, and so on. So there are two popular types, K-means and DBScan. K-means basically makes use of the number of K, that's the number of clusters which is given to us, and then it is linear. But for DBScan, we are looking at the density involved. So for instance, this is like an unlabeled data set, 5, and you have like 5 blobs of instances. So all these represent like a blob or a cluster. And if you are calculating K-means, it's just like a line of code using the instance of the K-means class. You put the number of clusters in there, and then you fit predict. So now we are defining the number of clusters from the onset here. And for K-means, you have to specify the number of clusters which we have here. You have to find blob center, right? And that's okay. You have to the instance label is your index of cluster. So because we don't have like a label for our instance, there is no black or white. So it's like an index 0, 1. So that's like the label of our cluster, and instances that are assigned to one of the clusters. So we can also look at the 5 centroids, and we can also plot the K-means, the diagram, which is also called vulnerable tessellation. So in this diagram, we can see the centroid, right? And for each of these points, it is calculated based on the Euclidean distance to this centroid. So now in this particular diagram, we have like 5 different clusters. And in K-means, we have hard clustering and soft clustering. So for hard clustering, we are assigning the cluster, the instance to a particular cluster. But for soft clustering, we are using a probability to assign it to a cluster, not just assigning it to a particular cluster. And how does Kmeans work? So this is like the 4 simple steps how it works. So we place our centroids randomly. So the first diagram here, we can see that the centroids are not actually in the middle of the blobs compared to the last diagram here. And then we label our instances, we update our centroids, and we repeat this step until we have this final output here.
Okay. I think that's good, so that when you're talking about Euclidean distance and instances and clusters, people can go on. Now you can go to the Gaussian.
Okay.
So guys, this has already been uploaded on YouTube for the last session, so you can catch up there and follow up. But
so when do we use Gaussian mixture? So whenever we hear probabilities and our data is our data set is not circular, maybe it has like a different random shape, then we make use of Gaussian mixtures. So, and the really amazing thing about this Gaussian mixtures is that it follows expectation maximization algorithm, which is a bit complex because it involves like lots of mathematical notations. However, we'll discuss this approach further down the line. Now, the next big question is, what is Gaussian mixture, right? So before I define this, let's consider the principle that governs this Gaussian mixture model. So now we have like a very big assumption in this Gaussian mixture model. So our assumption is that the model assumes that a mixture of Gaussian distributions is responsible to have generated the data set. So if you look at this particular X in X, right? So these are all the instances of this particular data set, and this is the Gaussian mixture, which is made up of like different normal distributions. So Gaussian distribution can also be referred to as normal distribution. So we are making this assumption in this particular algorithm, because ordinarily in statistics, if you follow this central limit theorem, if you throw a die repeatedly and you find the mean, you find out that the highest number that will occur will always be in the middle. If you look at this particular, let's say you have a value from 1 to 6 here, for instance, if you throw it repeatedly, you find out that most of the values that you get will be in this at this center. So Gaussian mixture actually follows the normal distribution. And the assumption that we're making is that in our data set, we have like lots of normal distributions in the data set. So now while we're assuming, okay, I've mentioned that, so let's go on. So now this is the definition of Gaussian mixture model, which we've covered already. Now, the good thing about this GMM is that when you observe an instance, you know that it was generated from a Gaussian distribution, right? But you are not told, and you do not know the parameters of this distribution. So you have like lots of distributions there, right? And these distributions, they have like different parameters. So now you don't know where does this distribution fall under, right? So now we have to fit the model by maximizing the likelihood of the observed data. Now, as the positive effect of GMM clustering, when they are done clustering, right, we get like a generative probability function that we can now make use of to generate like different samples of new data, new instances that were not previously in the trained sample. So let's understand the probabilistic process involved in GMM. So now each of these clusters that we have a mean and also a covariance and a weight. So when we're talking about K-means algorithm, we only talked about the mean. That's like the centroid of a cluster. But talking about GMM, we have a mean, we have covariance, and then we have weights. And since we have like a number of clusters in GMM, these clusters have different Gaussian distributions. Now, the weight determines the probability that an instance will fall inside a cluster. So let's take a look at the graphical representation. So if you look at this representation now, you would see that the square, let me see. The square represents the parameters, which is fixed. So you have the weight here, you have the mean, and then you have the covariance. right? And also looking closely, you see that there is a shaded portion here. So if you are trying to go through this process, you don't know the instances that you have, but you don't know the labels. So this shaded portion means that yes, you know your instances, but you're not aware of which of the labels or which of the clusters do this instance fall under. Now, before assigning a cluster, you must get these parameters right? So we have to estimate the number of clusters in our data set, but let's imagine we have 3 clusters. So I have n components here, 3, and this n10 means that I'm going to carry out this experiment randomly like 10 times so I can find the best one that fits. So after running this algorithm, I now have my parameter, I have my weight, I have my mean, and I have my covariance. Now, the next step is to talk about the expectation maximization algorithm. So now this algorithm is, like I said earlier on, is very complicated, right? But there are 2 principles that we need to know. So it involves assigning instance to clusters, updating clusters, and it also uses soft cluster assignment, which is a probability function. So when we are done doing this code, this particular code here, we can check if it actually converged and how many iterations it took. So we have 10 iterations here, but then it took 3 to converge. And for GM converge, GM is an instance of the GMM, the Gaussian Mixture class. So we can see that it actually converged, looking at it from here. So now that we know the number of clusters, right? 3 clusters, and now we know the size, we know the shape, and we know their relative weights. The next thing that we can now do is to try and assign these instances to these clusters that we have. So there are 2 ways we can do this from here. We can either make use of the predict function or the predict prober function. So the predict actually is add clustering. It assigns either 0 to 2. So earlier on, I said that these clusters don't have labels, right? So it takes the index of the cluster as label. So you can see that we have like 2, 1, 0, that's 0, 1, 2, that's like 3 clusters. And when you use the predict prober function, it returns like probability of each of the labels actually being in the cluster. It doesn't return like a cluster value. Also, I mentioned earlier that when you're done running this process, this clustering process using GM, you get like a model, right? And this model can be used on new instances that the dataset has not seen. So for instance, we have this new instance here, 6, that was generated there, and we can easily predict and try and cluster it to the existing function that was run on the earlier data sets. Okay. Now, another nice to have importance function of GMM is the ability to estimate model density for each of the instance given. Now, using the scores sample function or method, the log of the probability density function can be calculated and will be returned as the log of the probability density function when calculated will be returned as the density of each of those variables. So if you look at this diagram here, you can see that they are of different colors, right? And these colors represent like the different density contours of the trained Gaussian mixture model. So by default, let me see, not this. Yeah, so if you look at this example now, you can see that we have different colors, right? And you can see the cluster mean here. You can see the decision boundary, which is the dashed lines here.
Sorry, Toby. Sorry to
Yep.
Please, for this diagram now, if I was to represent it on the probability distribution curve, does it mean I have 3 Gaussian distribution curves?
Yes. So each of the clusters represent a normal distribution.
Okay. So it means the cluster is created by what do you call it? The probability distribution of the instances in a particular cluster. Is how the instances are clustered by the probability distribution?
Yes. So the GM contains like lots of normal distribution. So each of these clusters is like a normal distribution.
Thank you.
Okay. So now there is a really big problem with this GMM, this Gaussian mixture model, and that's the covariance type. So by default, when the algorithm runs, right, it takes any shape it wants to take. Why is this thing moving by itself? Okay. When the algorithm runs, it takes any shape it wants to take by itself by default. And sometimes when we have like lots of clusters and few instances, it's always good to define the shape we want to avoid the algorithm converging early. So some of the shapes that we have using this covariance type is we have the spherical, we have the tide, and we have dag. So these shapes have like different clusters. So if you look at this spherical, this is how it looks like. If you look at tide, this is how tide looks like. At this point, another question that I think we should ask is how do we detect anomalies, right? So one of the ways I think we can detect anomalies is by defining like a density threshold. So in this particular example, 4% was the density threshold. And when we define 4%, it means any point below 4%, right, is categorized as an anomaly. So that's why we have this light red stars here. So they are categorized as anomalies. So this is how we can detect anomalies using the Gaussian mixture. Now, if we can detect anomalies, right, that means we're given in the number of clusters that we need. So how can we get this number of clusters without just guessing? So there are two ways we can actually get the number of clusters that we need. We can make use of the Bayesian information criterion or the archaic information criterion, right? So these two methods actually, they return the same thing. They not that they return the same thing. They actually used the same way, but the only diminutive difference that we have is that in terms of fitting the data, BIC tends to be simpler. So if you look at this particular diagram now, so when we plot the information criterion with respect to the cluster, so here we are plotting BIC with respect to the clusters and AIC with respect to the clusters, we can see that there's like an elbow point, which is the minimum. So when it gets here, there is this sharp, what they call it, sharp
descent.
Yes. So so it's like the minimum point here, right? And that's number 3. And looking at BIC, you can see BIC is very easy to actually differentiate where it breaks and then rises again. But for AIC, it just keeps on continuing on that same level. So now this is another way of getting number of clusters. Now the beauty of using the Bayesian Gaussian mixture model to mixture function to get the number of clusters is the only thing that you need to do is you just need to have an idea of what is the maximum number of clusters that can be in the particular in this particular data set. So for instance, now we have like the maximum number of clusters that we think is 10, right? And then we specify the number of instances that it should run or times that it should like run. So after doing this, we can see that we have just 3 clusters here, right? So Bayesian Gaussian mixture function actually, you don't need to plot any graph to see where it suddenly breaks, right? But you just need to have an idea about the data set. So if you know that it can't be more than 10 components or 10 clusters in data set, specify 10 and then it does the mathematics for you and you have the number of clusters that you have. So here we have like just 3 clusters, 0.4, 0.1, and 0.4. And these values are like index values, not like actual values of the labels, because we have no label in unsupervised learning. Now, a weak point of Gaussian mixture model is when you are making use of it too. In Kmeans is just spherical, circular, right? But for Gaussian mixture model, it can take any shape they want to take. Now, the thing about this is if your data set has more than one shape, covariance type can allow you have more than one shape. If you're making use of there's a type of covariance type that you make use of that will allow your data set have more than one shape. But when you make use of such data sets, it doesn't fit with your data set. When you make use of such of shape and covariance shape, you won't get the actual it keeps some clusters for you. So in this example, the number of clusters that we have to have is not what we have here, because it tries to like it tries to have like different shapes for the data sets, for the clusters, not just one shape. So it doesn't fit a data set that has like different shapes. That's the weak point of mixture model. So if you want to make use of mixture model, all your clusters must have the same shape. Although it might not be spherical, but it can be other shapes, but all clusters must still maintain that shape. Now, other algorithms that we can make use of for anomaly. So one thing I failed to mention is difference between anomaly and novelty detection. So when you're using anomaly detection, after training your data set can contain outliers. And when you're making predictions, if a particular data is an anomaly or not, it makes prediction in your data set and also in the new instance that it has not seen. But for novelty, novelty works in such a way that it is sure that the data set does not contain any anomaly or any strange data. So it just makes prediction on the new instance alone. So for anomaly, outlier will be in the trained instance and test, the trained sets and the test sets. But for novelty, it will just be in the test sets. So there are other algorithms that we can make use of for anomaly and novelty detection. And these algorithms can take different shapes, unlike Gaussian mixture model that they have to take like the same shape. So we have the list here. And I think that's all.
Awesome, Toby. So this was this was a great, topic, and so unsupervised learning, like you said when you introduced this, it's about the cake, right? The big cake, right? It allows us to do a lot of data exploration. And when you're doing this machine learning project, like understanding your data, this has been the thing that why the focus we had for looking at the introduction to machine learning, understanding feature engineering. What are some of the things, like when you're going to a competition, what are you thinking about, right? So we saw quite a bit of use for this unsupervised learning, right? Especially when you're doing classification tasks, because when you're ensembling them, then you end up with a better performance, right? And we know that if you're doing, like, I know Chim and Zach are doing the challenge on Kaggle, the winning models will be really ensembling, right? So you have to start to think about what are some of the features and partitions of your data that you're seeing. So it will actually be interesting to just even run like an unsupervised, just feed the data and see what classifications it comes. Anyway, I think you've had me emphasize how important it is for, sort of duplication. Now, before we go to the questions, I think your presentation was super important to solidify some of the things around, because I was like, when I was reading this, I was like, oh, why again would I be using Kmeans versus something else, And, these are just slides that I found online, and I'll put them on Slack, is, like you said, we don't have any labels, and but we want to simultaneously label points and build a classifier. And so they give an example here for tomato sauce. So if you had a tomato sauce company that had brands and wanted to tailor their brands to sauces to fit their customers, so they ran a market survey where the test subject rates different type of sauces, and after some processing, they get the following data. So you can see these are more garlicky and more sweet. So people who like here would like more garlic and more sweet tomato sauce, but the ones who are here do not like, less garlic and less sweet. And so you can see that this tells us how customers like different data. And if you sort of think about this, you can see a company may say, how many different sauces should I make? How sweet or garlicky should these sauces be? And so we need to do what you said is a good function of customer segmentation, which is unsupervised learning, and to find what's the best sauce for each group and then focus on those. So let's say we want to have 3 clusters, right? And you put your X's wherever you want them to be. So, and then you can start to do, the K-means, but the K-means always assumes, so this is, you can see this is just your points here, and you can see these are the groups now, but now you start to see that you're, maybe you're fitting this, but these are quite distant, but you can start to see, okay, maybe these are my 3 clusters, and then you keep fine tuning them by trying to figure out what should be their centroids, right? Which is the map that you show, and what should be their boundaries, and understanding how many people are in that cluster. Now, the problem with this, K-means is because it has this spherical assumption that all our groups are circular, so like this. But if we were drawing these circular clusters, we know that that's not the reality, so which is why the Gaussian mixture models are important. And as you explained with the Gaussian probability, so it really took a while for me to understand that chapter. It was great to listen to you again, because it solidified where would you use sort of like the Gaussian models versus the K-means. Now we know the K-means is pretty fast. So the Gaussian models are very good, first of all, because you say maybe one source can belong to 2 groups, and that's when you start to find these probabilities, and you want to understand what's the mean, the variance, and then the density of the group. And so it allows us now to start taking different sort of shapes and trying to fit them. I think your last picture is much better, or I had one. So you can start to see something like this. So you just have these clusters, and like you said, within its own cluster, it will have its own normal distribution, but you can see where there are overlaps. And then we start to do anomaly detection on this. That's my own. I just wanted to go through it again, especially for the less technical people, because I spent quite a bit of time trying to understand it. Okay. So before we jump to questions, any comments?
I think I really like the learning more than K-means, because a lot of what I used to do was just anytime I used to mention cluster and it's K-means, cluster and it's K-means, but it's very nice to see other forms of cluster and algorithm and when to use them as well.
Yeah. Zach, any reactions to this?
Yeah, very similar. I had only really heard of K-means. I hadn't really heard of Gaussian mixtures at all. So just learning about that was really interesting. And I think it could be very useful, especially in the Kaggle competition that you were talking about, is like initially running those tests first and just seeing what, K-means outputs, what Gaussian outputs.
Exactly. Oh yeah, that would be great. Wamisha, I don't know if you had gotten up to this and had read this chapter or.
Okay, I've not read this chapter. I was still going over the previous videos for the other chapters.
Okay.
Here.
Okay.
Yeah.
No worries. Femi, I'm not gonna forget you, because Femi Kuti is one of my favorite musicians. So.
Okay. So I had of Kmeans, and then I think I started something on K, and then also I think neighbor crossfit. So I had like an idea, but I never had of Gaussian mixtures to date, so it was nice seeing how it works and how K-means clustering works also. So it was really insightful. Okay. And I'll definitely go back and read the chapter.
Yep.
Thank you, Toby.
Okay. Okay, Toby, do you want to go through the questions? You may have to remind us the answers.
Okay, so for me, my best part was actually getting the number of clusters using the Bayesian mixture model, because it felt really easy compared to using models silhouette diagram and the elbow points.
Yeah.
So like if someone can just actually make use of this formula and get number of clusters just from here, then looks and because for Gaussian it can also be circular too, like K-means. So if there is this method, I don't know, it seems like this should be like the go-to method for all clustering tasks from my own perspective.
Yeah.
So the first question, how would you define clustering? Can you clustering algorithms?
Do we just unmute and talk, or?
Yeah.
Okay. I think defining clustering is sort of grouping the set of unlabeled data points based off either a shared feature, based off some shared thing, based off something they share in common. I think we've all talked about a few clustering algorithms, K-means, Gaussian, and there's the other one before. I had a question, sort of like, so if you remember, there was one after K-means.
DB-scan.
Pardon?
DB-scan.
Yes, I was wondering how that one would compare to Gaussian in terms of like, what do you call it?
Speed.
No. In terms of like, K-means. So right now we have two that can sort of like overcome that problem of K-means being circular and linear. So which one when would you use one and when would you use the other? I understand when to use Gaussian over K-means, but I wasn't sure when to use Gaussian over the DBs.
Yes, so from my perspective, true, because even Gaussian, so we have density. So yeah, I don't know, honestly.
It's okay. I'll check.
I'm personally looking online. I mean, it's a good question, right? So I knew that my understanding was, so the article, you're all gonna explore this together, right? So the article that I find here is, so DB-scan is simple, blah, 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 blah. But you remember when we started where they just said the no free lunch theorem, which is just saying that you should try as many things as you can till you find the one that gives you to the truth, right? You remember that when we started reading the book. And so, so there are situations where DB-scan is very performant, while the others are bad. So density clustering seems to be better. And so, and density clustering use the point of reachability. How many neighbors have a point within a radius? And so DB-scan doesn't need a parameter K, which is the number of clusters we're trying to find, which K-means needs. So when you do not know the number of clusters hidden in the data set, and there's no way to visualize your data set, it's a good decision to use DB-scan. And so DB-scan will produce a varying number of clusters. And then obviously K-means is faster, but DB-scan doesn't require the number of clusters. So I think this is more of like, if I was thinking of like, if I had a data set and I wanted to start exploring, and you completely didn't know about this data set, maybe DB-scan would be the better one. And then once you have the number of clusters, and you remember that DB-scan did not give you probabilities or an output, you have to embed it with another model, right? Do you remember this?
Yeah.
And so then at that point, you would then move on and find out how your K-means, maybe because you have a better sense of clusters, although we went through how to find the clusters in the last presentation, and maybe have a sense of that.
Thank you.
So what are some of the main applications of clustering? Search engines, image segmentation, anomaly detection, novelty detection, etc. The next question is describe two techniques to select right number of clusters when using K-means.
So I think here we had those two diagrams. I remember them. I know where they are. What are the names for them?
Using the silhouette score.
Yeah, the
diagram and the elbow points diagram that plotted the inertia with respect to the clusters. And what is label propagation? Why would you implement it and how? So when we have a data set that we don't have labels, we have like partly labels and the others are not labeled, then we can make use of representative. We can make one of the label represent the others, right? And we can now propagate the label to the other instances that don't have labels. Right. So it's implemented when we have like semi-supervised learning, when we have some labeled and some not labeled.
And do you remember this was like the example where they show the means data set, right? So if you didn't have all the labels, could you start to figure out what's at the center and use those as the representative labels and then keep propagating them, right?
Yes.
Yeah.
Can you name 2 clustering algorithms that can scale to large data sets and 2 that look for regions of identity?
Definitely the one with mini batch. I think we talked about mini batch Kmeans algorithm. That one can scale. Because I think that was the purpose of it.
Of which one?
The one that can scale to like large data sets, right?
Yeah.
And then there's another mini batch, the other mini batch one as well.
For density, I of DB scan.
Yeah.
But for the ones that can scale, I don't know if Gaussian can scale.
I
think it'll probably be along the list of, I remember your slide with the list. With the one you did last week, it might be there.
Maybe bet should scale.
Yeah.
Okay, so let's just go through the question.
So
next one.
So Kmeans and BIRCH scale well to large data set, and DBScan and mean shift look for regions of high density.
Can you think of a use case where active learning would be useful, and how will you implement it?
I think it's just the same thing that you talked about, label propagation, right? So when you have plenty of unlabeled instances, but labeling is constantly. So in this case, rather than randomly selecting instances to label, it's often preferable to perform active learning where human experts, interact with the learning algorithm, providing labels for specific instances where the algorithm requests them. And I think people did this, right? So I remember you talking about this, or I was thinking about this. So where let's say you have a few data sets, you label them, you show the cluster, and then I say, oh, this is number 9. Then you keep going, and then ultimately you'll have a large number of labeled data sets without using too many people.
Yeah. What is the difference between anomaly detection and idiot detection?
I think normally you have the outlier in both the training and test data set. Vulnerability, it only occurs in the test data set. The instance only shows up in the test data set.
Okay. What is Gaussian mixture and what else can you use it for?
So GMM is probabilistic model that assumes the instances were generated from several Gaussian distributions whose parameters are unknown. So the assumption is that these groups are grouped into a finite number of clusters, each with an ellipsoidal shape. But the cluster may have different ellipsoidal shapes, sizes, orientations, and densities, and we don't know which cluster belongs to what. So the model is very good for density estimation, clustering, and anomaly detection. But I think the simpler way is K-means for more spherical when you know the number of clusters, or you think you may have an idea of the number of clusters, but Gaussian when you have a big sort of a data set that you have to sort of, I didn't mean being big, but I meant like a data set that may have a different distribution.
Okay, and 2 techniques to find the right number of clusters when using a Gaussian mixture model. That's the AIC and BIC, or we can make use of the Gaussian mixture model function. I think that's all. The other exercises there are practical, so I just skipped them.
Yeah. Well, so let's say thank you to Toby. I know he's super busy with a new job and we still see the same picture in his
Thank
background.
you.
So it's not been improved, but so we know that he's been busy, so we appreciate you taking the time.
Appreciate it.
Yeah, so this marks the end of the traditional machine learning topics, right? So now the next week, so you know, Femi and oh my God. Bamishe is, you need to watch back the videos and catch up, okay? Because you're starting to change gears. What I wanted to do, but I won't be able to do it next week, is to do like a recap of the first chapter of the book, right? Like what we learned, and maybe use some practical examples. In fact, if I didn't know better, Zach and Chima have been, maybe they'll give the next recap, because they've gotten very good at understanding how to present results, how to read results, how to investigate when your model is going wrong, which are very good skills to have, because you can troubleshoot your model's failure. But, you know, we have quite some power. We have a lot of data sets, you know, and know, like, you know, so I want to do a recap at some point, and it may be that when other people come on, people like Elmira, so that we can catch them up, but I'll start working on that. Next week, Nazanin had said that she was going to be presenting. I sent her a message, so I hope she's going to present. Else, if she's unable to present, then we'll push it towards one more week. I'll be away on Saturday, but we should still keep going with Nazanin if she's able to present. The next topic is introduction to deep learning, with something that's very commonly used, Keras, but I think this is going to be very interesting in terms of just understanding deep learning and the concepts and, you know, writing code. I still encourage people, I keep saying the same thing, you need a blog. You know, I say this personally to Toby, Chima, and Zach. You know, you always need a blog, because you learn something new and you experiment on it. So for example, if you go and say, I'll take this data set and I'll try it, or like this week when Chima, your model wasn't performing well, and we started to figure out how to investigate that. Those are very good blog posts. One, because the internet algorithm, I mean, you only game it by providing it more content, you know, and so first, if you can explain something to someone else, so we know that, you know, we have 2 new students today because Toby decided to go back and redo the book club to other people, you know, and that I think solidifies on what you've learned. And so if you write it down and keep experimenting, you will get better. And that's the beauty of this. And now we're starting to form a group of people where you can come together and work together and solve problems together, which is how I like to mentor peer students together. And so, you know, I'm just putting that as a challenge. We're going to be changing the vision quite a bit next week. And I'm excited about the deep learning portion, but this is also super important, okay? Okay, so you know my usual drill. I'm gonna go down from top to bottom and harass everyone. Abigail, any final, are you still with us or you left?
No, I'm still here. I'm still listening. Yeah, I will definitely go back and look at the previous video of chapter 9. Yeah, the recording. And I am set to go. Thank you.
Awesome.
Thank you, Toby, for a good job.
Yeah, Toby is like rocking this. Chima. What's?
I'm good.
Oh, okay. Okay.
I want to actually start. I'll probably launch. I'm thinking of launching the blog this weekend. So.
I already sent you what to use. It's very simple.
Yeah.
To use. It really is very simple. And so I think the next topic is actually the training deep neural networks, which is introduction to artificial neural networks with Keras, which is going to take 2 weeks. But training deep neural networks, it will be the subsequent one. Do we have volunteers to take that? I'm looking at you, Zach. Can you start working on that?
I can do it.
Okay.
Yeah.
Yeah.
So chapter 10.
That's chapter 11. So we have
Chapter
Nathan
11, okay.
coming to do 10, and maybe you can do 11, if that's okay.
Yeah.
Or
Sure.
you can pick any chapter, but okay. And then I know, Chima, you're working on the feature engineering, which is the other book that we are reading, and we'll present it through our lab meeting. But that talk has to be like close to 1 hour. So you need to like understand it and condense it.
Oh yeah.
Okay.
No,
Okay.
I'm ready. I've already finished the first chapter. I finished the first sort of intro one.
Okay, good. Okay, and please put the link of the book. I put it previously, just repost it so that the other people know on the channel which book we're reading about feature engineering, and so that people are ready for the discussion. Okay. Zach, did you learn anything?
Good, I think. Yeah, definitely. I never really considered using clustering algorithms for classification, so I think that'll be definitely something to try in the Kaggle competition and maybe even on the our current project and see if
absolutely.
that helps at all.
Yeah, absolutely.
I did have I had a quick question about ICU data.
Yes.
Currently, so the only data that I've seen is like ICU stay, but the Facebook model predicts mortality as well as intubation and any kind of adverse event, as well as if you need oxygen over 6 liters. So, but the only data I have is for like ICU stay, which is only one of, it's like 5 of the 20 labels that the model predicts.
So how about this? Send me the specific labels on Slack, and we will have to either curate our own data set to extract those labels, or I'll get someone else to do that. But yeah, that's it. Okay, awesome. And I know you have still something to work on because you're also working on the Kaggle challenge and you're doing the networking stuff, right?
Yeah.
Like as I work on the data set. Okay, good. Bamishe. I'm gonna get good at this. Bamishe, did we lose you already?
No, I'll stay here. I have a little issue with my webcam.
Okay, no troubles. But did you learn anything today?
Yes, I did. So in fact, surprisingly, I was reading a book, the theory of the Bayesian theorem, actually, and then seeing it here talking about the probability and how they actually came about it, picking between 0 and 1 and using it as the basic probabilistic models. So it's actually like gives a connection with this Gaussian mixture. So I also go over it again and gain more understanding. Thank you very much, Toby.
Thanks. Femi.
Okay, so I think I already mentioned things I learned today, but I'll definitely pester Toby to make sure that he gives you my email so I can get it to the group and see what books have been read and try to catch up on the videos. I think I probably do more books than videos. I don't know. I think I find it easier reading than watching the long video. So I'll try and make sure I catch up, and by a couple of weeks I should be on the same page as everybody.
Okay, awesome.
Thank you.
Okay. Wishing everyone a good week. Toby, you have the last word.
Last word. Okay. I honestly don't know what to say.
Oh my. Okay. Fine. We'll forgive you because we know you're freezing. But maybe once you guys can get vaccines, you can come to Atlanta, which is a little warmer. So thank you everyone for joining, and thanks Toby again for just a fantastic discussion. And look forward to the next week and the next phase. Hopefully we'll see people experiment a little more on their projects with the techniques that we are learning, and then they can report to the group, which is pretty interesting, you know, and that's specifically for you, I know, Chim and Zach, because you're doing a lot of experimentation right now. Okay. Everyone have a good day and talk next week.
Thank you.
Bye.